I am so glad to see you all here tonight. Thank you so much. This has been such a great joy for us to share our excitement about this great possibility, maybe this ultimate of all questions. And so I want to echo Umar's thanks to all the people who have helped put this together. And on behalf of the Alternative Earth Astrobiology team, I would like in particular to thank Umar and all the people in the CNAS Dean's office, including former Divisional Dean Cindy Larive, who is now our provost, for their support and I would say unbridled enthusiasm for astrobiology and the pursuit of this really important question of whether we're alone. And so Umar mentioned a release today, and if you blink, you miss these things. They come so fast and furiously. So there were two papers that came out in Nature, the prestigious journal today, and one was about data that have come from plumes of water coming out of the icy moon of Enceladus, and they were found to be very rich in hydrogen. And so that may not mean very much to you, but what it speaks to is the possibility of these reactions, for example, something called serpentinization in the crust of Enceladus, that are producing through abiotic, non-life processes, this essential ingredient of life, hydrogen. And so there are communities that can not only survive, but thrive on hydrogen, and they can do that in the absence of life. And so we see, as of today, the possibility of the central energy driving force for life in a liquid water ocean on Enceladus, the possibility of that. So these icy moons are fantastic targets. The other paper was about the persistence of plumes coming out of Europa, an icy moon of Jupiter. Now that's an exciting target because Jupiter's a lot closer than Saturn. Enceladus is around Saturn. And so there's always been concern that we wouldn't be able to fly through a plume in Europa because they were patchy in their distribution in time and space. But apparently they persist, and apparently we can identify them and fly through them. So extraordinary times. Those of you who have experienced the past lectures will know that our research group is particularly keen to explore other Earths lurking in our galaxy, the so-called exoplanets. To do that right, our team needs to collaborate with scientists such as tonight's lecturer, Antígon Segura. Antígon is an astrobiologist and a planetary scientist who works on photochemical models of terrestrial atmospheres. She's particularly interested in planetary habitability, remote detection of life, and early conditions of our own solar system. She may be the only scientist in Mexico, or anywhere in the world for that matter, with her particular and special blend of expertise and educational background. She earned a bachelor's degree in physics, a master's in astronomy, and a PhD in earth sciences in Mexico before serving 2 stints as a postdoctoral fellow in astrobiology in the United States. The first was at Penn State in their Astrobiological Research Center, and the second was with the Virtual Planetary Laboratory that I now have an affiliation, and others in this room do as well, one of the really exceptionally talented groups in exploring for life in exoplanets. And at that time, it was based at Caltech, NASA JPL. Now it's based at the University of Washington. Antígon is now based in Mexico City in the National Autonomous University of Mexico. Her visit today, among many other things, exemplifies the University of California system's efforts to foster collaboration between scientists in California and Mexico. And such things are supported by the UC Mexico Initiative and the UC Mexis program, which my own group has benefited from, among many other opportunities. We hope this will be the first of many visits by Antígona to our research group and her students to work with our Alternative Earth Astrobiology team. And we are just so thrilled that you're all here to help me welcome her tonight for this wonderful speech. Thank you so much. Antígona.
Thanks a lot. Thanks for the invitation. I have to tell you that I was about not coming. Yes, because of politics. But finally, I decided that it was much better to come here to stay protesting in my office where nobody would know about my protest. So thank you very much for the invitation, and you have a beautiful campus. I have enjoyed, well, I have been here just for 1 day, but I have enjoyed a lot. So let me move this. Okay. So extraterrestrial life, when we think about that, Usually we have images like this one that should appear in any moment. No. La, no, no. Okay, let me go here and move it. So we have this kind of image. Yes, E.T. So witches exist too, right? Because this is what we see in movies. The extraterrestrials are all colors and sizes. But when scientists think about extraterrestrial life, one of the main components that we need to understand are planets, because planets are the places where life evolves and starts. So we need to understand how a planet works, what kind of planets can be habitable. So I'm going to talk to you about planets that may be habitable. The first thing is how many planets we can have in our galaxy. This is our galaxy, it's the disk of the galaxy. And what we know is that there is at least 200 billion stars in this galaxy. And maybe most of them may have planets. Why? Well, the reason is because planets and stars are born together. They are born in these sites in the galaxy. They are called molecular clouds. The molecular clouds are made of the leftovers of the stars at the final stages of their evolution. Have you heard this saying that stars, that we are made of stardust? Well, it's actually leftovers of the stars. That's the truth. Is it working now? Okay. So these molecular clouds are made basically by two things. One is gas. Oh, perfect. Let me take the other one. Thanks. So one is gas, and the other one, yes, it's dust. The gas is mainly hydrogen, but it has water too, and organic compounds. These organic compounds are made of carbon, and by reactions in these clouds, and some molecules are so large that have 70 carbon atoms. They are called fullerenes, and they look like football, soccer football balls. The dust is made of silicates. Silicates is what Earth is made of. So the dust is silicates, graphite, which is a form of carbon, but not organic, and ices. The ices can be water or CO2 or methane, depending on the temperature. So what happens is in these clouds, sometimes some parts of the clouds become very dense and they collapse and they form protoplanetary disk. In the middle of the disk, in the middle of the disk, the star is formed. And in the disk, from the material of the disk, the planets are formed. The way it happens is that the dust starts to grow because the dust starts to stick together, and it forms larger and larger rocks until they form planets like Earth. Or if the rock is very, very large, it can accumulate gas from the disk and then become a gas giant like Jupiter or Saturn. So this is the way the planets are formed, and because the planets and the stars come together, basically most stars in the galaxy may have planets. So that's a lot of places to look for. These planets are called exoplanets or extrasolar planets. Right now we have about almost 4,000 exoplanets detected in our galaxy. The first one was called 51 Pegasi b. Let me tell you something about how we named exoplanets, because naming 4,000 exoplanets, it's not that hard, actually. So if the star, it's called, like, I don't know, 51 Pegasi, then the first planet we find around it, it's called 51 Pegasi b. The next one is 51 Pegasi c, d, and so on. So the star, it's 51 Pegasi, and we found, or the first planet we found was called 51 Pegasi b. This was in 1995, and as I tell you, we have found almost 4,000, and we keep looking for more planets in our galaxy. The way we find these planets, it's in different ways, but I'm going to talk to you about 3 ways to find planets. The first one is called the radial velocity method. How it works? Well, the thing is, when we think about a star and planets, we usually think that the planets go around the star, and the star is basically quiet, looking at the planets around it. But in the systems, in the physical systems, when we have 2 bodies, or 3 or 4, or more than 2 bodies, actually what happens is that all the bodies in the system circle around one point that is called the center of mass, which is this one here with an X. So if you have a planet, the star is going to go around this point, and you will see it. If this is your telescope, you will see the star going far away, coming closer, going far away, and coming closer. And there is an effect called the Doppler effect, where you have something that is sending waves, sound waves or light waves in this case. So when this object is coming closer to you, the waves are shrinked, so you look at different light. And then when it goes away, the waves are wider, so you look different, the light of the star. What happens is that it goes bluer and then reddish and bluer, depending if the star is coming towards us or far away from us. And from this light, we can calculate the velocity of the star. The velocity of the star is directly related to the mass of the planet that is actually pulling the star. So if the planet is large enough to make a huge velocity in the star, then we can measure it, and we get something like this. So we can measure the mass of the star, the mass of the planet, and we can measure how much time the planet takes to go around the star, because obviously this is related. Oops, that was, I'm sorry. I was going to, okay, this is the pointer. So this, it's directly related to the time that the planet takes to go around the star. So with this period, we can calculate then the distance between the star and the planet. We have another method to find planets, and this is the transit method. It's basically an eclipse. So the planet goes in front of the star, and some part of the light of the star is blocked by the planet. So what you would see is that this is the light of the star, and suddenly it drops, and then goes up again. How much light is blocked from the star depends on the size of the planet, how large it is, its radius. So we can calculate the radius of the star because of the dip of this eclipse. And how much time the eclipse lasts, it is directly related to how much time the planet takes to go around the star. As you can see right now, we haven't seen the planet. We see the star, and we see what the planet does to the star. It pulls the star, and then the star wobbles, or it covers the star, and then the star is a little bit less bright. But we haven't seen the planet. And the reason why it's so hard to take pictures of planets is because planets are very small and very faint. It's just like having a lighthouse and having a bug over there. Do you see the bug? No, you don't see it. Of course you don't see it. Well, if I turn off the light, You can see it right there. There is a lightning bug. So you may think that, well, the bug was very close to the lighthouse. But the thing is, when you have a planet and a star, let's say Earth and the Sun, if you go far away from the system Earth-Sun, these 2 points are going to look closer and closer and closer until you cannot distinguish between the two of them. And the thing is that one of those points, it's billions of times much brighter than the other one. So that's the problem. We can have pictures of planets in very special cases right now. The case is when they are very far away from the star. These are the planets of HR 8799, that's the name of a star. And these are 1, 2, 3, 4 planets around the star that is covered here by the instrument. So if we have the Earth-Sun distance, and we call it 1 astronomical unit, then this planet, the closer one, is 14.5 astronomical units. The next one is 27, 43, and 68 astronomical units. Just for comparison, the distance between the Sun and Jupiter is 5 astronomical units, and between Sun and Neptune, which is the latest, is Pluto a planet now? Or yeah. I don't know what. But it's Neptune, the last planet, it's 3 astronomical units away. So you can see that these planets are very, very far away from its star. And then we can take pictures of the planet. Okay, so the other thing is where we can find these planets, because as I told you, these planets are very fine, so very hard to see, very hard to detect in general with any of the methods we have. So this is, again, our galaxy. If you were a light, you would take 100,000 years to go from one side to the other side. And we are right here. Do you see that? The point? There? This is us. And then this circle, that one, is where we can see most of the planets. So basically, that is the solar neighborhood. It's like 3,000 light years away. So we are not going to find habitable planets or life in the galaxy or the universe. We are going to search for life there, the solar neighborhood. Okay, so the next question is, what are these planets made of? Well, let's see the planets of the solar system. We have 3 flavors of planets in the solar system. The first ones are made of rock. There. The first ones, these ones, Mercury, Venus, Earth, and Mars, all of them are made of the same things. They have a core made of iron, and then a cover, a mantle, made of a mantle and a crust, made of rock, silicates. Silicates are a combination of silicon and oxygen. Then we have these big ones, Jupiter and Saturn. They are made basically by hydrogen and helium. They are not gas giants, because the gas phase is just a small part of them. Actually, the hydrogen inside these planets, it's something weird that we call metallic hydrogen. The hydrogen behaves like a metal. The metal, it transports heat and electricity. That's what the hydrogen does inside these planets. And the last ones, they are very similar. They are made of ices, water, ammonia, methane. So we have these 3 flavors of planets, but we have another kind of bodies in the solar system. These are, okay. These are the icy satellites that go around these giants. And these planets are similar to the terrestrial planets, the planets made of rock, but they have ices too. So they can have like half and half of ices and rock. So we have all these types of bodies in the solar system. The exoplanets, well, we haven't seen them, I told you, but we have models. We can guess what they are made of using models. So let's say that we have a body made of rock, only rock. I can calculate what is the radius of that planet if it has different masses. So for example, if I have a 10-mass planet, the radius is going to be like 1.5 Earth radius. This is Earth radius. And if that same planet with 10 masses is made of water, only water, then it's going to be larger. So I can build these models and then put the measurements of mass and radius of all the planets I have. We don't have that measurements for all the planets, but we have for many of them. So we can guess, it's not guessing actually, we can say what kind of materials are made of. The thing is that most of the planets we have found actually don't look like anything we have in the solar system. They are right in the middle of these two. This one, the Earth, is 1 Earth mass, and this one, Neptune, is 14 Earth masses. We don't have any planet that has 2 or 3 or 10 Earth masses. None. But those planets are common around other stars. So what these planets are made of? Well, we have several choices. One, it's a larger version of this one. We call it super Earth. It doesn't have powers. It's just a big rock. And the other choice, it's a small version of this one. It's mini Neptune. But we have another choice. Actually, when you have these ones, you can have atmospheres of CO2 or hydrogen atmospheres. So they are really different kinds of planets. And the other kind of planets you may have, it's an ocean planet, a water planet. I think you already heard about those kind of planets before, but let me tell you a little bit. How much water has the Earth? A lot? Members of the faculty members, please do not say anything. But is there a lot water, lots of water on Earth, or just a few? Lots of water. Okay. So this is all the water that we have. It's less than 1% of the whole mass of Earth. Okay. It covers a lot of the surface of Earth, but it's not that much. Actually, as you can see, Earth is a rock with a little bit of water. When I'm talking about, it's planets that may be 10%, 50% made of water. So something like, I don't know, some people may remember this planet from Dunes. So this is a water planet. Well, maybe there is planets like that. So there are other kinds of planets we have found. For example, rocky planets are very close to their stars. This planet, Corot 7b, it's rocky because we have calculated the models, and we know it's rocky. This is not a photograph. This is, of course, a artist impression. And what we know is that the planet is so close to the star that the temperature must be like 2,000 centigrades. I know you are not very used to centigrades, but it's very hot. So for that temperature, the rocks are melted. What means is that all the vapor coming out of the rocks, the rocks become gas. So they go up and they cool and they rain down. So you have a planet where the rain is made of rocks. You've seen this planet before in some movies. Of course, there was we don't think there is Jedi's over there. There are another kind of planets, for example, the planets that go around two stars. And this is amazing because we have to explain how these planets form. And this is a challenge for the scientists. We have seen this planet before too. We have planets with two stars. We don't know if it's habitable, but we have these kind of planets. And then the ones we are interested on is the habitable planets. That's why you are here, right? And usually when you think about habitable planets, this is the picture. Yeah, another Earth. And you may see this news, and scientists found a planet like Earth. And what most people have in mind is something with water, blue skies, maybe grass, maybe cows. But this is not what we refer to. When scientists talk about a planet like Earth, it's a planet that has the size of the Earth or the mass of Earth. Or maybe it's a rock, a little bit larger, a little bit smaller, but a rock. In that sense, it's the same as saying a Venus-like planet. Venus and Earth are very similar in size and in mass, and they are basically rocks, both of them. So that's what we refer to when we are saying we found an Earth-like planet. Because we don't have the tools yet to see if these planets have water or atmosphere or gas or cows or anything else. So we are going to look for habitable planets. What we mean with habitable planets, not Earth-like planets, habitable planets. Well, let's go back to Earth, because when we talk about habitable planets, this is the only one we have right now. This is the only one where we know there is life. And we have to make the best generalization of life we can out of this one example. How we do that? Well, all the life on Earth is built on carbon. Carbon has a special property that no other element of the periodic table has, that it's able to, silicon has a little bit something similar, but we have problems with silicon. But the thing is that carbon can bond with 4 different elements, including itself. And then it forms very complex molecules that can even replicate themselves. These molecules need an environment where they can move freely, but not that freely, because if they are in the atmosphere, for example, they move around too quickly and they are not able to find each other. So they need this environment to move around and to congregate. What is this medium? Well, it's water, liquid water. It could be another liquid, but in the case of Earth, it's liquid water. Now, this is the generalization of life. When we say we are looking for life like the one on Earth, we are talking about carbon molecules and liquid water. And this has another support, and that is the astronomical support. Because as I showed you before, the planets form where there is a lot of carbon and water. So it is not very much hard to think that maybe other planets will have carbon and water, and life is going to be made of those 2 things. So let's say we are looking for this kind of life. Carbon is the 4th most abundant element on the universe, so we assume it will be there. But liquid water is a little bit more difficult to get, because it depends on the special conditions of the formation of a planet. So we need a planet that has liquid water on the surface if we want to look for life in another planet. Because if life is not very obvious in the surface, then we cannot detect it. So we need water in the surface. So basically what we can say is, okay, you put the star. If the planet is very close to the star, it's too hot, the water is going to go away. If you put it too far away from the star, then it's going to be very cool. And if it's right in the middle, there should be a place around the star where the water can be liquid. But you need two things for this. First, you need a surface, so to put the water on. So you need a rocky planet. The other thing you need, it's an atmosphere, because the atmosphere provides the pressure you need for having liquid water. And the other thing you need is to have the warm planet. If we don't have any atmosphere at all in the Earth, actually the temperature would drop for 30 degrees, right? Well, in that sense, centigrades are 50, 60 in Fahrenheit. I put the two scales there. So you need the atmosphere because the atmosphere keeps the warmth of the star using greenhouse gases. So actually, greenhouse gases is what make our planet habitable. The atmosphere we are thinking about is not oxygen atmosphere. It's a CO2 atmosphere because that's what the volcanoes emit. So the volcanic gases is the one that build up the atmosphere of the planets. So that could be CO2 or hydrogen if the planet is large enough. So our habitable planets are rocky planets with atmospheres that are in some distance to the star where they would be warm enough to keep liquid water in their surface if the water is present. So all those conditions should be met in order to have a habitable planet. How many of those we have? Well, we don't have any habitable planet, actually. These are potentially habitable planets. So they may be, perhaps, we don't know. And the reason is because we know, for some of them, we only know the mass or the radius, but we don't know if they have atmospheres or water. We know the distance to the star, we know the mass or the radius, but we don't know anything more. So we cannot say right now how many habitable planets we have. We can just say we have potentially habitable planets. So what is our plan? Well, the plan is to take some of those potentially habitable planets and observe them with the next generation of instruments, like, for example, the James Webb telescope. The James Webb telescope, it's a 6-meter telescope that is going to be the next Hubble telescope. It's going to be around the sun, not the Earth. I think it's going to go out by the end of this year, right? The next year. They have been moving the date, so I don't know where they go now. So next year is going to be out, and if we have enough hours to look for a planet, then we can pick up the light of the planet. Basically, the visible light and the infrared light. And with that, we can say what the atmosphere, if it has an atmosphere, what the atmosphere of the planet is made of. The way this works is that the stars hits the planet, but when it illuminates the planet, some part of the radiation of the star goes back to the space. Some other part of the light of the star reaches the surface, hits the surface, and then the planet emits infrared light that we cannot see, but it's light. And when this light goes away to the space, the molecules of the atmosphere take some of the colors of this light. So what we end up seeing is this. This is a spectrum. So these black lines here, these lines here, these peaks, are the colors that are taken by the molecules of the atmosphere. So, how do we find life in other planets? Well, is anybody sleeping now? Well, the next 3 slides are the important ones in this talk. So please wake up, and I tell you when to go back to sleep again. Okay, so this is a spectra of Venus, Earth, and Mars. What you are seeing here, this is, sorry. What you are seeing here is how bad I am to manage this. Lab? Okay, there, great. So this is the amount of light that is reflected back to the space. So for Venus, it's almost 80% of the light that receives from the sun goes back to the space. For Earth, it's about 30%, and for Mars, it's about 20%. And then there is these peaks. This is colors. This is infrared light. This is visible light. And you can see these peaks over here. So this is the absorption of CO2 molecules, carbon dioxide. So this atmosphere is made of carbon dioxide, that one too, carbon dioxide, all of it, it's carbon dioxide. Because the atmosphere of Mars, it's transparent, we can see the iron oxides in the surface. And then here on Earth, we can see these big holes in the spectrum. This is water. This is the absorption of water. It's not the water in the surface, it's the water in the atmosphere, because there is so much water in the surface, it forms vapor, and the vapor in the atmosphere is the one who is absorbing all this light. And then there is this peak. This one, right here. That is oxygen, right? O2. Where the oxygen comes from? Where? Okay, let's see. The Earth was formed 4.5 billion years ago. Life on Earth appeared around 3.5 billion years ago. Yep. Back then, there was no oxygen in the atmosphere. There was only nitrogen, CO2, carbon dioxide, water, but there was no oxygen, because oxygen is not produced by volcanoes. There is a little bit of production by chemistry, but it's not important to accumulate oxygen in the atmosphere, so there was no oxygen in the atmosphere. But then, life happened, and in particular, these guys called cyanobacteria, microbes, they started producing oxygen. So they use light for having energy. They have CO2 and water. They took hydrogen from the water, carbon from the CO2, and a little bit of oxygen. And they didn't need that much oxygen, so they throw away the oxygen. The oxygen is like the leftover of these guys. So they made the food, and they put away the oxygen. And they contaminated the Earth for the first time. It was huge. The geologists call it the rise of oxygen. The biologists call it the holocaust of oxygen. It was that bad. Most of the species, none of the species back then, used oxygen. They used on other sources of energy, like methane, sulfur, iron. They could eat a lot of stuff, hydrogen, but they didn't use oxygen. The oxygen has this problem that oxidizes organic material. So if you are made of organic matter, the last thing you want to find is an oxygen molecule. But the thing is that, this reaction, oxygen and organic matter, you can get a lot of energy out of it. So what we do now the animals, the ones, all the multicellular organisms, what we do is to eat organic matter, right? And breathe oxygen. The oxygen combines with the organic matter, and you have a lot of energy. Actually, that is the only way to keep working on these machines that we are, with many cells. The only way to provide energy for them is with this reaction. So these guys change the life on Earth and change Earth itself. Because now we have a planet where there is 21% of oxygen, from none of it to 21% in the atmosphere. They change the whole atmosphere. So what I am saying here is that this signal that you can see with a telescope was produced by microorganisms. So the unicellular life can change a planet, and we can see this change from far away. We don't need to go to the planet. We can see the atmosphere of a planet and detect the changes of life on that planet. So we are not looking for anything that is going to eat us, or cute, or that uses lightsabers. What we are looking for, actually, is for those signals that the unicellular life can produce on a planet by changing the surface of the atmosphere of the planet. So for now, well, just to be clear, so for now, this is the only planet we have with life. We haven't found life anywhere else, not in the solar system, not elsewhere. And you are wondering why we want to find life if we cannot take a picture or grab it. Well, we cannot go to these planets either. If we ever have the technology to go to these planets, we are not going. We are stuck here. So this is the only planet we have. Why we are interested in finding life on other planets? Well, it's the biggest experiment we can make. This is the first time in human history when we can make this experiment. We can actually answer the question, are we alone? Of course, it's just for the neighborhood, but at least it's something. So for finishing this talk, I would like to say there is a lot of, we heard a lot this thing that we are finishing with life on Earth, right? So we are ending everything. Well, that's not exactly true. Actually, we may kill all the mammals, a lot of other animals, reptiles, maybe not the insects. But yes, we are capable of exterminate a lot of life on Earth, but not all life, not ever all life. If you go to a lake that is contaminated and you took a little bit of that water that you cannot drink because you would die, if you take it to a microscope, you will see that it's full of life. Life can live in hot places, cool places, in volcanoes in the floor of the ocean. Life can live from hydrogen, methane, sulfur, rocks. So the life on Earth that has been here for 3.5 billion years is not going to go away just because we contaminate the planet. It's not. So what we are really ending here is the conditions that support human life. That is what we have to be worried about, because we are fragile. So you can imagine this. You can imagine this species that was able to put robots in other planets, like Mars, like the moon. We can think on this species that was able to conquer the oceans without being able to breathe in the water. We know how the smallest particles of matter are made. We understand how the universe was formed. We understand what the stars are made of without even touching them. So we are this species that is capable of all that. But we have the tools to extinguish ourselves too. The good thing is that nobody would notice, so you can go in peace to your home. Thank you very much.
Thank you very, very much for that great talk. So now is the time where we can take some questions, and there are, per normal, there are microphones on both sides, and they should be turned on now, and so I'll ask you to come down and speak into the mic and ask your questions. While people are coming down, I'm going to go ahead and take the privilege of asking the first question.
Thank you.
And so we talk, you've all gathered from this wonderful talk that we're looking for the compositions of atmospheres and the gases within those atmospheres that can be convincingly, or at least we hope somewhat convincingly.
We can wait until
I'll wait just a second. Fingerprinted as biosignatures. So the question is, you've mentioned oxygen, and within our group and many other groups, what we all do is put our brains together and really imagine what that headline is going to be in 10 or 20 or 30 years. And so I'm going to put you on the spot and ask you what you think the gas will be, or combination of gases, and how certain we will be that those gases are actually uniquely from life or may have alternative explanations, including the possibility of oxygen coming from the breakdown of water having nothing to do with life. So what's your best guess?
Actually, that is our problem right now, because we have basically two possible biosignatures that are strong enough. That is oxygen and N2O. And the other thing is that, the atmospheres of exoplanets, there is a high probability that they are made of CO2. And Earth's atmosphere was full of CO2 for a long time, 2 billion, 3 billion years, almost 3 billion years. And there was no signal of life during that time. Right. Just a little bit of oxygen, just a little bit of methane, but we didn't have any. So we are trying to make tricks, like, for example, sulfur compounds. But it's certainly not an easy question. And then there is the observations, because what I show you there, it's a spectra of planets that are like very well, like lines, beautiful. But what we are going to see, it's points here and there in a graphic, and then huge error bars. So we will have some kind of so how confident we will be on the measurements depends on those error bars and the retrieval we can do, and how many scenarios we have beforehand, so we can test. Let's see if this goes with the spectrum we have measured or not. So I would say that it's going to be a long way until we have better and better telescopes, and we have better models and imagination to picture all the things that can happen to a planet.
So if I could ask
I don't have.
if I could give you your wish, and you could identify one gas or a combination of gases, what would you measure with confidence?
I would say methane. Planets make methane anyway. Well, of course CO2, because we need to know if there is an atmosphere. CO2 and water, that means the planet is habitable. I need those two. Okay. So those, and maybe, yes, oxygen and methane. Okay. So those will be my best guesses.
Okay. Let's take a question over here.
Oh, can you hear me?
Yeah, get close to the mic if you would, please.
Can you hear? Okay. One of your slides earlier had an Earth similarity index, and I saw some of the planets on there were more similar than Mars. What goes into determining that score?
Well, that is a score made at the University of Puerto Rico by, I will get the name of the researcher who does this, but it's highly controversial. You can just get like the parameters you would like and just say like if it's the mass and the size and the distance from the star and the likelihood that it may have water and all. So we don't have to take it that seriously right now. It's an indication that helps us to choose some of the best candidates. So that's what I can tell you about this index. I use the picture usually because it's very nice. They produce beautiful graphics, so that's why I use it. But basically what I use the most for them, these planets are in what we call the habitable zone, which is the most important part, and their sizes or their masses indicate that they may be rocky planets. So that's what we have now.
Thank you.
We'll take a question over here.
What would you do once you found a planet with life on it? I mean, obviously you described the whole motivation behind it is for the pursuit of knowledge, but how would that discovery lead to more discoveries? I mean, what new knowledge would be gained once you find a planet with life?
Well, the first thing is that we would know that life is not some kind of weird phenomenon, but something that happens, the matter organizes given certain conditions that are not very specific, it's just general conditions. And the other thing is that we can ask for more money to make larger telescopes, because then we see, we find it. We just need to see closer. So that's, and then, I don't know, we really don't know what we are going to find. So we have possibilities, but
Thank you.
we don't know. You're welcome.
I'm going to do it with this audience. I've done it in the past. So that if you've been to most of these talks, maybe all of these talks, one of the things that's come very clearly through all of it is that most of the focus is not on a search for intelligent life, right? So that can be done. Groups like SETI have focused on those kinds of signals and not found anything. And so what we're really talking about are the gaseous metabolic processes of microorganisms. And so I'll ask you, as I have in the past, how many of you will be excited when we make a headline announcing with 90% certainty, confidence, that we've identified methane on a planet 10 light years away that is biological? Does that excite people? And that's fantastic. And I'm so happy to see that, because in my opinion, we're going to have that happen, and I hope it's all in our lifetimes. And I'm delighted to know that it's not going to have to be a rerun of their television shows or a little green something or another in an image. And so that's fantastic. And let's go over here for another question.
Will the James Webb telescope be able to let us distinguish if the potentially habitable planets are truly habitable?
We hope to. We have some problems. Telescopes work this way. You have to ask for the time. So you put a proposal, and then that proposal competes with other proposals. So basically, we need like 200 hours to look for one object. So that's a lot of time. And cosmologists and other people is not going to be happy about it, because we are going to take a lot of time with the telescope. So we have to convince them that this is a very good challenge to solve. But yes, I mean, according to our models, James Webb is good enough if we have enough time to gather the photons of the planet. And we have two closest, we have Proxima Centauri b, which is the closest star, and therefore we have the closest planet. It's 4 years light years away. So we are not going to get anything closer than that. So that's a good candidate, and we are very happy about it. Thank you. You're welcome.
Over here.
Hi there. My question was, I remember you mentioning before on one of the previous slides that there are two elements that can kind of support life, one being obviously carbon and the other one being silicon. From what I've read, hearing that silicon could be a type of element that can create life, the life would be kind of rocky-ish. What would a planet like that would hold that type of life kind of look like? Like if we were to look out into space and see that planet, what would we be looking at? The environment?
Rocks. That's a problem with silicon. I mean, what we see with carbon is that everywhere where carbon is, it makes complex stuff. Those molecular clouds I show you, they have 10 Kelvin degrees. So that's 10 degrees above the absolute zero. And over there, the carbon is already making stuff, interesting stuff. And silicon is making dust and rocks, and bigger rocks, and larger rocks. So we don't have any evidence that silicon can form, can have this I don't know how to say it in English, malleabilidad, the possibilities that carbon has. So that's our problem with silicon. And then it needs other type of liquids, which are the reason why we love water that much is because the range of temperatures and pressures where it is liquid, it's very large. That doesn't happen with all the liquids. If you have something like methane or other kind of liquids you may think of, for example, in Titan, there is liquid methane. And you have carbon there, a lot of carbon. You have methane. But the range of temperatures of pressure where it becomes gas, it's very small. So that's the problem. See, that the conditions where silicon can form interesting things are so limited that and it will be hard to tell to NASA that we are going to look for something that looks like a rock. We actually don't know how to make the difference. We are trying to fight. I mean, it's not fighting, but it is a challenge already to understand how the carbon life is going to look like. So the answer to your question is we have no idea. Yes, thank you.
Thank you.
Let's take one over here.
Hello. Okay, how long do you think it will take mankind to identify a habitable planet that could become the first candidate for like a planetary kind of colony that we can go to and establish ourselves there?
I don't think we are going to ever make that. So, this is the opinion of a scientist. That doesn't mean that's a scientific fact. So let's be clear on that. Yeah. The thing is that in order to go to other planets, we need a lot of energy to go out of here. And if we spend the energy bombing other countries, we are not going to have anything for going out of this planet. So this would be a collective enterprise. Otherwise, we are not going anywhere.
Awesome. Thank you.
There's a lot of talk about colonization, but what we have is Mars, right?
That's the closest one, and even for that, it's expensive.
That's right. Let's take maybe two more questions. One over here on my right.
What planet will you start your observation? What planet will you search for life first?
Sorry, let me again. Sorry.
What planet will you search for life first?
Oh, well, in the solar system, we are already on Mars, but it's not working that well. We know that Mars had habitable conditions a long time ago, but it doesn't seem like it's not habitable right now, and we haven't found any evidence that there may be life right now on Mars. So we have Europa, which is this moon around Jupiter, and we just have news about Europa, and maybe there Europa is made of it's thick ice, water ice, and then there is an ocean of water. In the bottom of that ocean, maybe volcanoes, like the ones that we have here in Earth, and maybe life there. So we don't know yet, but we can explore that ocean. And I am hoping for Europa, actually. Other planets outside the solar system, that would be Proxima Centauri b. That's the exoplanet of the closest star to Earth. So we are hoping for that one too. But the star, Proxima Centauri, it's a very crazy star. It's small and it produces flares all the time. So we don't know if it already killed the planet before. So we don't know that. So it will be an interesting target. Did that answer your question? Yeah.
Thank you.
Thanks to you.
Let's take one more question over here on my left.
Oh. You can get closer later, and
Yeah.
I'll.
So at
Yes.
the end, you are welcome to come up and ask your questions
Yes,
one-on-one. So
please
don't
do
go
it.
away. But one more over here.
Is the presence of a magnetosphere to protect the atmospheres of exoplanets a concern that's being addressed, or do we have the instruments to detect magnetospheres in faraway planets?
Yeah, that's something. Okay, the quick question is we don't know. Okay, but it depends. What kind of a star are you around? Because if it's a star like the sun is not really that much of a big deal, actually. You can see Venus, for example, has a huge atmosphere, and the atmosphere is going to be there, whatever the sun does. But the thing is that there are some stars, these smaller stars, the M dwarfs, that are very active and they have flares all the time. For that, you may need this magnetosphere or a huge atmosphere. But I mean, the models, it depends who you ask to. Some model says that you really need a huge magnetosphere, and some others say, well, you don't really need it if you have this size and this type of atmosphere. So we haven't come to a conclusion yet, but actually Proxima Centauri b is one place we cannot detect the magnetosphere. But we can see if the planet has kept an atmosphere or not, and being around an active star. So we have some kind of test over there. But it's an open question.
Well, I wish we could keep going on, and I hope that people will come up at the end and ask your questions, and we welcome that. But I want to do two things. First, we will have the raffle, as per usual,
yes.
and they are lovely prizes. And those of you who stick around benefit because many of the numbers have left the room. But the other thing is that I say with some sadness, some significant sadness, that this is the end of what has now been 10 lectures. We had 5 here and 5 out in Palm Desert. And it's been quite an extraordinary experience for me to share with you the excitement that I feel and that we all feel here at UCR. And we hope that you all have left knowing things that you didn't know before, and will leave with a great sense of wonder. And I've even hypothesized that maybe 10 or 15 years from now, maybe even fewer years, there'll be a big slug of school kids in Riverside that are applying to study space science or astronomy or earth science because that seed was first planted at the lecture series here. And I know I was impacted in similar ways when I was a child, and I hope that we have that effect. And so I want to personally, and on behalf of a very large group, thank you all very, very much for making this a very special experience. Thank you.